Thank you for coming. Thank you for joining. I had a nice lunch, and I hope that you had a nice lunch as well. At least for me, it revitalized me a bit in the second day of intensive talks and a lot of information. And it's nice to see a couple of familiar faces that I've already spoken in the last 2 days. Let me move a bit back from the audio here. My name is Daniël Kok, and I work at Alliander. I'm a software engineer and developer there. You'll hear from me on mostly the second half of this presentation, but I'll leave everything to Anna for the introduction and the first half. So, thank you.
Thank you, Daniel. So my name is Anna van Velsen. I'm a data scientist at Alliander. As a data scientist, I help our asset managers to move from continuous or static limits to cyclic or dynamic rating of assets. I work in a team is founded about 2 years ago, and since then we're developing thermal models to reach this goal, to find these new asset limits. In this role, I joined a workshop last winter, and during this workshop I talked to my fellow colleagues, also data scientists, but from other DSOs. And they were quite interested in our thermal models, but at that moment I was not able to share these models with them. We could talk about it, but I could not give them our models. And yesterday we learned, and we already heard it a lot today, less talking, more coding. So coming back to Alliander, coming back to the office, I decided to let's make an effort to open source our thermal model so we can share our code and can work on it together. So what you will learn today is how we make our power grid sweat, but maybe also how you can make your power grid sweat as well. You already saw some other colleagues from Alliander maybe talking about our congestion problem we have in the Netherlands. And we like to show you as well what's in the news about this problem. Because the problem we're actually doing this for is that we have quite long waiting lists due to net congestion problems. And the costs are increasing, and solutions we're trying now do not seem to work enough. So, and people are also told, the consumers, that they should move along with the weather, as it's stated here, to save costs. But yeah, but that's not enough to solve this congestion problem, right? So at Alliander, we're working on strategies to solve this problem. One of them is expanding the grid, meaning building new substation, putting bigger cables in the ground, and maybe new transformers. And another way to solve this is by utilizing the grid better, or better grid utilization. And this means that with the current grid, as it is there now, we try to help more consumers to connect to the grid. And this means that we need to put more power through the grid with the assets as they are now, they're designed as they are now. So, showing you this map to see how big the problem is, and also to show you that it's not only a problem of one DSO, but for more DSOs. But also that red means that the grid is full, so no people are on a waiting list to get their connection. And meaning full is that these assets we're talking about are up to their limit, which is a power limit or a load limit, which follows from maybe the type plate of these assets. But these assets, and this is a subselection of our assets, for example, transformers, bare conductors, switchgear or cables, all these assets also have their thermal limits. And increasing the load of these assets, we expect that they're quite warm, because also this map is red, so we expect that these acids also might reach their thermal limit. But if you have a look at these acids again, for example, the oil of one of our transformers in a distribution grid, we see that they're not that warm. So these temperatures are allowed to rise up to above 100 degrees Celsius. And that we see that most of the times these transformers are not that warm yet. So actually many grids seems to have some more capacity left, like thermal residual capacity, which we can use as well. And that's where we are working on. Our asset managers have the goal to fully utilize our critical assets under acceptable accelerated aging. And we want to do so before 2030. And that's coming quite fast. But there are two topics very important to realize in this goal. One topic is, or questions actually, what is fully utilizing these assets? What does that mean? And this aging, how do we know how much they're aging now? And both of these questions, these are answered by looking at the temperature of these assets. I already heard it today that asset managers or utilities are very risk averse. And that's also important to know when you're working on increasing the load for these assets. So what we are doing is, by increasing the load, we're increasing the number of faults. And we know that aging will go faster. But how much? We could monitor all these assets. So we could put sensors on the cables, put sensors in the switchgear, in the transformers. But that takes much time. It's costly. And we need hands to do so. And from all of these, we don't have enough, because we also need to expand the grid. So why not use thermal models to monitor or to calculate how warm these cables and transformers are getting, and calculate how much residual capacity there is in terms of temperature. If we know this, we can increase the loadability of these assets. And as is stated above, there are also risks involved. So how better we can do this, so how better our thermal models will become, the better we can do this cycle again. So we know more about the risks involved, and we can advise our asset managers better on which loadabilities to use for their assets. So to go back to this goal, I really want to emphasize that to know what is fully utilizing, you also need some information on the temperature of your assets, and also for the aging, because it's temperature rise is a major influence on that. And this is the point where I want to ask Daniel to tell something more about our thermal models we have.
Thank you. So, as Anna indeed mentioned, thermal models are essential in this part to be able to determine what kind of limits we can reach. So let's take a look back at the assets that Anna briefly showed already. This wasn't a random selection of our assets. So just to list them, these are the transformers, the bare conductors, switchgears, and cables. And these are assets that we are already thermally modeling within Alliander. The team that Anna and I are working in was established 1.5 years ago to mainly focus on the three on the left. There's a separate team on the cables, and our main focus is transformers as well. Let's show these assets as a small example how they look like in a field, and the best place to take you there is with a substation like this. In this substation and with our assets, there are two important things that I'd like you to think about here. And that is that the first thing, if we look at the schematic overview of a substation, all these assets are interlinked with each other. So I think that you already know these kind of symbols, but just to touch upon them, each symbol that you see is a different kind of acid. All these acids are interlinked, all right? Then the second important thing that I'd like you to know is that all these acids have different limits. And these limits are these blue bars that you can see right here. And these limits, as Anna already mentioned, are thermally limited by their thermals. What does this actually mean? Well, to go into detail to there is that these acids warm up when you put some load through them. And these have stuff like isolation paper. When it gets warmer and hotter, this isolation paper degrades. And it cannot hold the load that is supposed to be able to carry. This is this aging that we're talking about. When we start to reach the limit of this acid, then it will degrade faster, so our acid will get older quicker. This is what we need to get in our head. Since these acids all have a different limit, and since they are all interlinked, there is a limit based on this entire chain, and that is the lowest and the weakest link. This limiting acid is most often a power transformer in this case, or a distribution transformer. So that's why I want to take you briefly to determining thermals of a transformer. It is limiting in the most cases. This is why we focused within our team on building a transformer thermal model. And luckily we didn't have to start from scratch. A thermal model already existed. This was built by the International Electrotechnical Committee, or IEC for short. They are focusing on building norms, and the one that's listed right there is one that includes a thermal model for transformers. Well, I will spare you the details of the equations. We're all in the second day right here, but you can look them up right there, and I'll touch upon some sources that you can look at the end. What I want you to know right here is that this model is schematically shown like this, and the thing that we need is the thermals of a transformer. Those are way on the right there, and there are two output values that we want. The first one is the hotspot temperature, and this is the most important one and the most critical one. This is the one inside the transformer, close to the windings, and this is the spot where it gets hottest, the name says it. The thing is, this is the most difficult one to measure. More easier to measure is the top oil temperature that you can see right there. And the top oil temperature we can also simulate with this model. And since we measure that at most locations, we can then easily derive it and double check it by simulating these both. To then have an input for our model, we need to know a couple of things. Of course, we need the load profile of our transformer. This is what is going into the transformer and can vary from something like a day, or a week, or a year even, or longer. We usually take a week if we want to be quick, because those include the most patterns for us. We also need to know what kind of transformer we're dealing with, so we need its specifications. This is often the most difficult part. We can find most of the specifications on the spec sheet of our transformer, but luckily the IEC has thought of this, and they include a handful of typical transformer specifications to work with, and in our model we have included these defaults as well to get a really quick start. But we also make a couple of specifications mandatory to make sure that you are really thinking of what you're doing with the model. And lastly, the ambient temperature profile. Because if a transformer is standing on minus 20 degrees outside, it's obviously going to be capable of handling a way higher load than if it's standing inside an enclosure with 40 degrees Celsius inside. And then all the magic happens inside this big red box, so I won't go into detail right there, but feel free to check it out in the norm as well. What I want you to know as well is that this transformer thermal model is something that we've built over the past 1.5 years. We took our time here to test it and to validate this model in our own power grid, and that's what takes the most amount of time. We can't just measure only in the winter, for instance. We need to time this also with the summer. So that's why it's taking a bit longer than just implementing the code itself. So By using this thermal model, we can then look towards newer limits. And Anna briefly mentioned this, but I want to emphasize it again. This is going from static limits to cyclic limits, to look at the potential areas where we can increase the limit temporarily for different flexible contracts, for instance. So this model we can then use to, as I said, determine cyclic limits or to scale up the static limit of our transformer. The way we do this is by closely measuring the results, by calculating what kind of thermals are happening under its current load. Then if it does not reach its limit, we scale up our load and calculate again. And we repeat this process until we reach a certain limit where we think, all right, this is an acceptable area where we can increase our transformer to. So we did this with our assets in mainly most of the critical areas in our substations. And by doing this, we calculated the potential that is in our grid. And using thermal models, we have found that there is 600 megavolts ampere of potential inside our power grid by scaling up using thermal modeling. For me, this is a number where I think, wow, 600, that's big. But I can't really relate to that. I'm not really close to the megavolt ampere world. So I'll take you back to the map that Anna already showed you to give you a bit of a perspective of what this number means. And to do that, I'll take you to a place of great importance to me, Deventer, which is where I live. And Deventer has roughly 100,000 households. And if we go to the lower estimate of 600 megavolt amperes, then we have a potential of 100,000 households. These are households with an EV, cooking electrical, solar panels, stuff like that. But if we take it more optimistically, we can even go as high as 200,000 households. The other thing that I want to mention here is that Deventer does not lie under the jurisdiction of Alliander. So again, I touch upon the point that we are not the only ones with this problem. We have an entire country here with multiple DSOs that we're wanting to work together with. As Anna already said, this was difficult in the past, but Jonas has greatly helped us and our OSPO team to eventually go open source. And this is what we did 3 months ago, and by doing that, we've made some workshops for developers, but also for asset managers themselves. Bless you. And we have in 3 months made some great progress already. I'll briefly touch upon that, because going open source, we shared data of different transformers to validate the model even further. Because as you've already noticed with the first panel yesterday, that data is the most difficult and precious resource that we can have. We had our first contribution from another DSO. This is also really cool because that shows them that they want to use this model and that they want to improve on it. And it already happened in 3 months. And we also start in our conversations with a TSO to discuss what kind of features would you like to see in this model to be able to use this. So it's already flowing up inside the Netherlands themselves, and we're slowly but surely wanting to reach out to international parties as well. And by telling you this, I want to emphasize to you that this is possible and that there is potential in the grid. So I'd like to briefly recap upon what you've heard already, because we're already reaching the end of the presentation. There is potential in your power grid, and you can determine this by the thermals of your assets. And it is difficult to measure, so you can thermally model them. And that is possible already. So the main thing that I can give you right now is to give our transformer thermal model a try and to see what kind of potential is in the power grid right now for you. And with that, I'd like to finish and thank you all for your attention. Thank you very much. Oh, yeah.
Sorry
No problem.
for raising question before you ask for it.
Yeah, no, that's great.
I come from Siemens Energy, so we are a vendor of transformer. So we do maintain our own thermal models and also maintain the public models like the IEC ones you are running. I have one question about the transformer that is monitored over 1 or 2 years, right? Is that a dry type or oil type? Does it have like forced cooling on and off? Are the cooling strategies considered in the thermal model, or it's just recorded as part of the data? Thanks.
So do I understand correctly if your question is about what kind of transformers we can model? Yes, at the moment we can model power transformers and distribution transformers and all oil-filled transformers. And at the moment we have ONAN, it's forced cooling or passive cooling. And what Daniel mentioned, like we're working together to new features. Very soon there will also be a 3-winding transformer available as well. But there we have need help on validating because we don't have so much data on that. And together with the 3-winding, we're also going to work on a planned feature is the switch type of cooling. And also a feature is, help me here, tap changes.
Oh, tap changes, yeah.
Yes,
yeah.
so.
Yeah.
Yes, so there are more features to come, and I think we will announce this, or we already had on our GitHub discussions page. So I will switch to this page as well. So if you go to our GitHub page, there you can find a link to the discussions and the documentation. And if you have like questions about it, you could also do a feature request there, and we can talk about it there. Or yes. More questions? Oh.
So I wonder against which reference model you are validating your results?
Do you know this?
Like a reference model. We know there's also IEEE model. Also open sourcely available. I think we're planning to compare it, but I think they have I didn't dive into that yet, I have to say honestly.
The thing is also that we're building further upon what the IEC did. So if they have any reference models there, then I suggest to check out there. Sadly, the people that we have in our team to work on this are not present today. That's it. Yeah.
Yeah. For the rest, it's measurements we compare with. Yeah. So in field measurements. Yes.
Thank you for your presentation. I'm Alexis Frémont. I'm working at RTE, and I'm sure some of my colleagues will be very interested about the work, so I will talk about it with them. May I be so bold as to ask you, who is the TSO you've been working with?
It's Tenet. Yes.
Okay,
yeah.
you.
Sorry, we should have just put it on the slide. Yes. Yes.
More questions?
First of all, thank you for the presentation. I was wondering, how do you collect your ambient temperature data?
So what we do is use the temperature from our weather stations. So what we do for example, our power transformers are positioned outside, mainly, and then we just use a nearby weather station to get the weather. And we do so by using an open source project as well.
I forgot the details of which one we use, but we looked into more finely attuning to where the transformer is located, because one in a city center does not follow the weather reported by the KNMI, which is the source that we are using. which is often outside the city center. But when investigating this, we found that there is little to no benefit by using this as external temperatures. So the KNMI is really easy to use there, and that's what we use for ambient temperatures mainly. Yeah.
That's the weather provider API, but I guess it's only relevant for the Netherlands, but you should check. Yeah, but we have also distribution transformers, and they're placed in enclosures. So it could be a brick building or some other. There's a whole variety in kind of buildings around these distribution transformers. So this is also a challenge for us, how to use the ambient weather correctly, and then we plus up some kelvins to model this. So this is also a challenge for us in modeling these distribution transformers. It's also some interesting topic to look into the future if we can improve this. Yes.
Yeah. Any more questions?
I think then we wrap it up.
Yes.
And
Thank
we,
you very much for your attention, everyone.